Alright, ladies and gentlemen, here, consider this yourself being warned. This class recording has started, so if you say anything stupid that's loud enough that the microphone will pick it up, it will live forever on the internet. So think clearly, think wisely before you say something. So do you need to...
Hi, Hannah.
So, now everybody feels...
Are you sick at home?
Everybody feels welcome now. So. Alright, over the weekend, you guys were supposed to watch the video on graphing motion and talk about different types of motion graphs. And we talked in the video, I introduced two types of motion graphs to you guys. Position versus time, velocity versus time. So let's start with position versus time. And to introduce you guys to that, I gave you these two, or this graph that shows the position versus time graph for two swimmers. We'll assume the white one, the white cap lady, corresponds to the green line on this graph, and the yellow cap lady responds to the red line on that graph. So, let's do this. Okay, a position versus time graph, in my mind, should be able to tell you 5 things in total. A position versus time graph should be able to tell you 5 things in total. All right? What are they? Okay, so it can tell us the what? The speed, or maybe also the... Can we get more detailed than the speed? Well, let's go on this. Acceleration? Not quite yet. What is a more detailed version of speed? Velocity, right? So it can tell us the velocity of an object, and it tells us that by what? What tells us the velocity of an object on a position graph? What characteristic of the graph tells us that then? The slope, right? That's what I was going for. So the slope of this graph will tell us the velocity of that object, right? That was sort of one of the more difficult ones, right? Let's go more simple. So we know we can tell the velocity from the slope. Let's go more simple than that. What else can a position versus time graph tell us? Let's tell us information. Use it. Distance, right? It can tell us how far an object moved. It can tell us time, when it was in a certain spot. It can tell us where it was, right? So the 5 things in my mind, it can tell us position, where an object is, right? Just by where it shows up on the graph. It can tell us time, when an object was in a certain spot. So position, time. It can tell us displacement, which is the difference between where it ended versus where it started. It can tell us distance, which is the total length of the path. And then it can tell us velocity, which is the slope of that graph. Okay? Good there. Questions on that? Right? So position versus time graph. It tells us position and time, so where and when, but it can also tell us displacement, where did it start versus where did it finish. It can tell us distance, how far did it totally go, and it can also tell us the velocity, depending on the slope. Okay? Good? All right. If you would please, open up your book to page 56. Open up your book to page 56.
Can you tell Thomas the apple book?
Sure. Hannah, it's the Apple book. So, because it's only, yeah, sorry. Shoot. All right, on page 56, right in the middle of the page, is practice problem number 26. Why don't we start with that, all right? So it says a rose-covered parade float is at x equals 0 at time t equals 0. The float moves in a straight line at 2 meters per second for the next 5 seconds before coming to a stop. After a 5-second stop, the float moves again at 1 meter per second in the same direction as before. So part A says sketch the position versus time graph for the float. And then part B, determine the position of the float at 2 seconds and at 11 seconds. So, suggestion. You may do this on a separate sheet of paper, right? If you printed out the slides, to use while watching the video over the weekend, the back of those pages are probably all blank. You know, if you want to do that, if you want to do these problems there to kind of keep everything together, that might be a good idea too. All right. So, number 26 on page 56 asks you first to sketch a graph and then determine some things from that graph. So let's start with that. That's up to you. Mostly for this one, you have to write. It doesn't give, like, there's no axis drawn for you, right? So, I mean, it tells you here if it's going this, right? For this, I would probably recommend 1 second intervals on the time axis, right? And then here, right? To make your life easier, 2 meter intervals on the y-axis probably make the most sense. Okay. Say again? That's true, it does. How you do that is totally up to you. While you guys are doing this, I'm going to pause the video just for a little bit. All right, ladies and gentlemen, recording is back on. So, first, part A right here, it tells us to sketch the position versus time graph. Going back to, and I didn't tell you to pull this out, that's okay, right? This is our syllabus from the very, very beginning of the year, including the command terms that we introduced on Friday, right? This language of what IB uses to try and convey what they want you to do on their assessments. One of the things that it says is to sketch, right? So for sketch, it says represent by means of a diagram or graph labeled as appropriate. The sketch should give a general idea of the required shape or relationship and should include any relevant features, right? So let's go back here. First, all of our graphs look something like this. Okay? Starting off, right? Moves in a straight line 2 meters per second for the next 5 seconds. So that means that it's going to steadily climb by 2 meters on position for every 1 second that goes by. Right? I tried to make anything looks good, or I tried to make mine hit the key points that it's supposed to. So here, right? That should be 5 seconds, right? And if it goes 2 meters every 5 seconds, right, it should end up at 10 meters, right? Yes? So, what does the slope of this line have to be through this section right here? What does the slope have to be? 2, because the slope on a position time graph tells us what? Velocity, and it tells us, right, 2 meters per second is the velocity, right? After a 5-second stop, it's not really what I wanted to do. I want to underline it, not cross it out. After a 5-second stop, meaning during that 5 seconds, what is the velocity? 0. And that means that the slope of our graph during that time has to be what? 0. And that means it's a what? give you more of the horizontal line, all right? So there's a difference between a straight line and a horizontal line, right? Okay. 6, 7, 8, 9. Yes, all right. Yes, I'm trying to make my line go. So that means that during this section right here, the slope of that line should be 0 because that object is at rest. It's not moving. Its position does not change, right? But then the float moves again at 1 meter per second in the same direction as before. So, two things. What? 1 meter per second. How should the slope of this section of the graph compare to the slope of that section of the graph? Less, specifically, half as much, right? But also, if it's going in the same direction, what has to be true about the slopes? They're both positive slopes, right? Slope can be positive and slope can be negative, just like velocity can be positive and velocity can be negative, right? That tells us whether an object is moving in a certain direction or in the other direction, right? Remember, we use the positive or the negative to indicate direction. Okay? Good there? And then from your graph, determine the position of the float at 2 seconds and then at 4 seconds. So at 2 seconds, the position should be 4 meters, right? Or more specifically, we probably should label it as positive 4 meters because position is a vector quantity. It has direction, right? There's another 4 meters that's on the other side of where it started, right? And then at 11 seconds, it should be plus 11 meters? Yes? Does that make sense? Good. All right, good there. Okay. Next, if you would please, to continue on with position time graphs, flip your book to page 60. Page 60. On page 60, you'll see practice problem number 37, which has 3 parts. It shows you position time graphs for 2 cars, A and B. If you would please answer parts A, B, and C for that question. So page 60, number 37. Feel free to discuss with the person next to you if you need a little guidance, if you're not sure which direction to go. Yeah. I guess maybe you might just be getting sick. I have paper towels. That's all I got. They always want extra credit.
And give yeah.
Don't worry, the recording probably won't pick it up.
Oh yeah.
All right, so number 37, parts A, B, and C. I have labeled, or I have highlighted the correct answers for those 3 questions. All right, good there? Okay. The reason I bring this one up is because of this section of the graph, like here. Okay? First, what happens At that point, right there, the red dots,
Same place.
they're at the same place, right? They are the same position, okay? Now, let's imagine that, they're in different lanes, all right? So they're not running into each other necessarily, okay? All right, but they're in the same position. However, physically, what would we see at that point?
I'm at the same place.
They're at the same place, but what's going on? B's passing A, right? They are in the same place at that point, but two reasons we can tell that B is passing A. First, before that point, B's position is lower than A, and after that point, B's position is higher than A, right? But also, too, what else can we tell about these two cars just by looking at this graph? If we were watching them, what would we see? What's other information we could get off of this graph, Austin?
You kind of see car A going like 25 miles an hour and car B is going 60 miles an hour.
We don't know the exact numbers, right? But generally speaking, car B is going what? Faster than car A is, right? Because of its steeper slope. So make sure that we keep that in mind. During this yellow highlighted section, A is ahead of B position-wise, but B is catching up, right? Just because A is above B on this graph doesn't necessarily mean that A is going faster than B, right? In this case here, A is actually going slower than B, but B is catching up, all right? That confuses people sometime at the beginning because this line is above that line, right? That doesn't mean A is going faster than B. B is actually going faster than A because its slope is greater. Okay? Good there. All right, next, if you would please flip your book to page 68. Page 68, which is the end of chapter 2. And on page 68, you'll see that there are three graphs, case A, case B, and case C. You have them all in a straight line, but I couldn't fit them all in a straight line, so I broke them up like this. Okay? So number 78 on page 68 says, two trains run on a straight level track. The motions of the trains in three cases, A, B, and C, are described by the position time graph shown in figure 2.23, which is the three graphs that are right there. Right? In which case do the trains travel in opposite directions, get steadily farther apart as they travel, or collide? So answer those three parts there. We'll come back and we'll talk. They run into each other? All right, so use some color coding to hopefully try and get you guys to answer those questions, right? So first it says travel in the opposite direction. If we're looking for things that are traveling opposite directions, what should we be looking for? How do we indicate?
Opposite slope.
Opposite slope, right, or opposite sine slope, okay? There's two instances where the trains, or where the graphs have opposite slopes, right? Here, train 1 has a positive slope, train 2 has a negative slope. They both start on the same side of the reference point, but one's traveling farther away from the reference point, while the other one is traveling towards the reference point. But here, in case B, right, again, they have opposite slopes. Train 1 is traveling towards the reference point because it has a negative slope. Train 2 is traveling farther away. So both C and B have trains traveling in opposite directions, right? B gets steadily further apart. What should we be looking for here?
Steady
Steady.
slope.
Not necessarily speaking, not necessarily both positive. Here they are getting, in part A, they are getting farther apart, right? Because train 1's slope is greater than train 2's, so it's traveling faster, but they're traveling in the same direction. Here though, right, in case C, right, even though they're traveling in opposite directions, that means they're getting farther apart, right? So the separation between the graphs here and here, right, it's greater in the second case than it is in the first case, but the separation here and here, right, is also greater there. Nate, go ahead.
I wouldn't be.
I suppose you could say that, like, here and here and here, right? Although I kind of saved that one for part C, because what do we see about the two graphs in part C?
Maybe fine. I just think both of them.
Yeah, probably. Well, during this section, right, at the beginning, yeah, further on, yeah, that we see that going like that there, right? Although if
They're on the same track.
yeah, technically in this graph, right, this graph should, right, it should go like this and should go like this, and then it probably should flatline like that, because what happens in case B? They crash, right? And once they crash, right, where do they stay? At where they collided, right? So these two lines probably should come together, and then after the crash, they should probably both stay together like that. Austin, go ahead.
For case B,
Mhm.
what if you considered wrong if you were looking at like the way, like I thought you were like if you were thinking like the way that the graph showed how they started, they were going in the same direction kind of.
For B?
Would not the opposite, or would they consider that being the opposite because they collided? They wouldn't.
Right, which means which way do they have to be going if they're going to run into each other?
Sorry.
Okay. Now, I guess that's not necessarily true. If we go back here, right, A and B are both traveling in the same direction, because what do we see about both of their slopes? They're both what? What's similar about their two slopes? They're both positive slope. They're different positive slopes, but they are both positive, meaning they're both traveling in the same direction, but B's traveling faster than A, right? So they could run into each other even if they're not going in different directions. In this case, they just happen to be going in different directions, where eventually they run into each other. Okay. All right. Good with our position graphs. Okay. All right. The second type of graph that I introduced you guys to in the video is the velocity versus time graph, right? Oh, sorry. One other thing. Flip your book to, this is going to be a big jump. Hold on. Flip your book to page 109. Page 109. Oh, sorry, 110. On page 110, on the top right, you have the read, reason, and respond section. which is entitled BAM! Apollo 15 lands on the moon. So, on July 30th, 1971, Apollo 15 landed on the moon. So approximately 2 years after Apollo 11 was the first mission to land on the moon, okay, which was July-ish 1969, okay?
I always wonder why this skipped like 12 or 15
No, they didn't. No, they didn't. All those, well, Apollo 12 landed on the moon. Apollo 13 never made it to the moon. Did you ever see the movie? Yeah, yeah. Right. So the reason that they picked this one for this picture for this problem is because it relates to the graphs, right? Okay. So here it says, okay, that Apollo 15 is coming down towards the moon at a nice steady rate, okay? And you can see that at the beginning, because what do you see about its graph during that section right there? It's steady slope, right? But then, from this point forward, right, what do you start seeing with its graph? Is it straight anymore? No, not straight anymore, right? It's curved. And we said that if a graph is curved, and I introduced you to this in the video, right? What does that mean about its slope? Its slope is, generally speaking, what? Well, in this case, it is larger, but generally speaking, if a line is curving, is its slope constant? No, right? It's changing slope. And if the slope is changing, what does that mean about the velocity? It's changing as well, right? So the yellow section of the graph was a nice constant descent. That lunar module was coming down at a nice constant speed. But, you see right here, it says, engines shut off, okay? Which, you might think, oh, well that means it stops. But, if the engines stop, right, it keeps going, but what actually affects it more now? Lunar gravity, right? And gravity causes things to accelerate, to go fast. Well, I shouldn't say to go faster. It could mean slow down, it could mean go faster. We'll see that tomorrow, right? But in this case, right, it causes the lunar module to actually increase in speed. And as you can see right here, right, that line starts to curve. And so it starts going faster and faster and faster. Now, lunar gravity is much less than Earth's gravity, right? It's about a quarter-ish, a little bit less than a quarter-ish, about 1/6 actually, all right? But it still causes the object to speed up, and we can see that on this graph just by the curvature of the line, right? So as you can, if you read the little description here, the astronauts that were in there was like, boom, they like hit it. They're like, whoa, hey. It's kind of like when you, hopefully you've never had this happen before, but if you're like backing up and something, you like kind of hit something, you're like, whoa, what happened? Yeah, it's kind of like scary. It hit a little bit faster than they thought it was going to, and so they responded with the bam. So I'm sure you could probably find some audio of that. But I wanted to show it to you just because of from the graphing standpoint, right? This is a position graph. It's labeled as height, but that's position, right? So for the first section, it's nice and steady, nice constant rate. But then once the engines shut off, gravity takes over, it starts to accelerate. Okay? Good there. Okay. I think they might have shut it off maybe a little bit sooner than they thought they were going to. Because you can kind of see here, right? The height that it was off the ground was only 1.25 meters. So, I mean, it's only this far off the ground, you know? But it starts to accelerate. You were coming down at that nice constant rate, and all of a sudden you start going faster, and it's like, whoa, it just kind of caught him by surprise a little bit. So, all right, good there. Okay. Next part of the video, talk to you about a velocity graph. All right? And as its name suggests, sort of in an obvious sort of way, velocity can tell us two things, right? Or a velocity time graph tells us two things, right? What does a velocity time graph tell us in an obvious kind of way? Now let's go with not just speed, but velocity in time, right? what it's doing and when it's doing that. But we can also get two more things out of a velocity versus time graph. Yusuf, what else? Acceleration by measuring the what? What feature of the graph tells us the acceleration? The slope of a velocity graph tells us acceleration, okay? But then we can also figure out what from a velocity graph? The displacements, right? And, right, so, right, slope on a velocity time graph tells us the acceleration, but, and like I said, in no way intuitively I would not expect you to figure this out intuitively, but if we figure out the area between the graph itself and the x-axis, so in this case, for this simple kind of speed graph where it's just going faster and faster and faster, okay? If we figure out the area of this triangle, it will give us the displacement. How far does that object go during that time? That's one thing that's a little more confusing in this graph than it is in other graphs, right? For instance, if you would please flip your book to page 91. Page 91. All right. Here on page 91, let's take a look at number 41. Okay? So, Devin, this is a great transition that we just made right there, right? So, here we have transitioned from a position time graph to a velocity time graph, right? So we have to make sure when we're interpreting these graphs, we know what type of graph we're talking about, okay? Here, this object goes up, right? Or sorry, the graph goes up a little more, and then comes back down. Okay? However, because of the different features of the velocity graph and what it tells us as opposed to a position graph, what's going on, the motion of this object is different than what a position graph would tell us. Okay? First, straight lines. But on a velocity graph, what does that physically mean? It could. It means acceleration, right? Physically, from here to here, what would we see that object doing? Speeding up, right? Physically, from here to here, what is it doing? It's not slowing down. Its velocity is still getting bigger, right? Those values are bigger, but it's not as fast. It's still positively accelerating, but it's not accelerating as much, right? My example I like to use for this is, so if you're getting on the highway, right, you start at the top of the ramp, and at the beginning of the ramp to get on the highway, you're not going very fast, right? You just made the turn, you stopped, or whatever it was. If you look at your speedometer in the first 5 seconds, it might jump from 0, no, it's like 3 seconds, it might jump from like 0 to like, I don't know, 30 miles per hour. That might be an exaggeration, but go with me on that, okay? Well, let's say, okay, the one example I always use is over by Dave and Buster's. You know how if you're coming up Sperry, do you have this picture in your mind? No. Like, do you know where Outback Steakhouse is?
I don't drive there by myself.
Okay.
But,
okay. Do you know where it is?
Say something like that before.
Well, the reason I use this example is because, like, all right. So here's Outback Steakhouse, okay, and then there's a road that goes like this, right, and then it kind of curves around like this, okay, and then this is Columbia Road. Yeah, there's like there's hospital right here, and then Dave and Buster's is like back here, right? Does that sound familiar or no?
I don't drive a lot.
Okay, anyway. The reason I use this example is because this is a bridge, and the highway
I know.
is underneath it. Okay. So, but here, if you come up here, there's a stoplight here. Oh man,
You need yellow one.
I did. I just didn't hit it. So. Okay, so, but so you can get stopped at the stoplight right here. So you're stopped. But if you go straight, you'll get onto the highway. So you can be stopped at the very, very top of the ramp, and then you can go. Okay? The first 3 seconds, you go from here to here, and your speedometer might increase from 0 to 30. Then, but 3 seconds down here, your speedometer might only increase from 60 to 65. We're still getting faster, but just not as much. Okay? But then, during this section right there, what's happening?
Tires broke down.
Let's go generally speaking. What's happening to your speed or your velocity during this section?
Slowing down.
It's slowing down. But, Devin, back to your original question, your velocities still have what sign? Same direction. We're still moving in the positive direction, but we're getting slower. So you would still be moving forward, just not, you're slowing down as you're moving forward. So we have to keep that in mind as we examine these graphs. Okay? You'll get a chance to do that in lab tomorrow. All right, real quick, for tonight. All right. There is homework on the calendar for tonight. There is there's one problem from your IB book, but there are several problems from the Apple book. The answers are posted for the Apple book problems, all right?
Bye, Hannah.
If you would please, make sure that your Apple books end up back in the cabinet so they're not out for the rest of the class. I would appreciate it.